A quick little video about some patterns in Pascal's triangle and some nice combinatorial identities we can realize from it. So first of all, I think you guys should have seen this at some point, but this is Pascal's triangle. The whole idea is you start with a 1, and maybe we can say, and then 2 1s, and kind of you put a 1 down each side as follows, and then to get the next entry, you just add the 2 entries above it. For example, 1 plus 1 is 2, so we put a 2 there. 1 plus 2 is 3. 2 plus 1 is 3. Let's do down here. 6 plus 4 is 10, etc. So maybe if you're kind of unsure how to do this, maybe pause the video now and see if you can work out the next row in Pascal's triangle, and I'll write it in. Okay, so the next row is going to be, we have a 1 there, and then 1 plus 6 is 7, 6 plus 15 is 21, 35, 35, 21, 7, 1. So that's how Pascal's triangle works. But of course we can think of this in terms of binomial coefficients. So we can indeed think of this as kind of like we have a row of 0 things, here's a row for 1 things, here's a row for 2 things, here's a row for 3 things, 4 things, 5 things, 6 things, 7 things, and we can continue on. So let's say this entry here, and this is kind of how it works, maybe let's do the third row. This is saying how many ways I can choose 0 things from 3. And this entry here we can think of as saying, well, this is how many ways we can choose 1 thing from 3. And we can continue that idea for all of this. In fact, this is kind of working as a recursion. So we start off with, let's say here, this is 0, choose 0, that guy there. And we always have, for each first and last entry in a row, we can think of it as, let's do, maybe I'll do this in blue. So we can think of, let's just say a row here. So we can think of these entries. So we can think of this guy as n choose 0, and this guy as n choose n. So the first and the last ones. And you can see what's going on if we think of this in binomial notation when we say, let's add the 2 entries above to get the entry below. Well, this is, and it's pretty easy to see this, if we're adding, say, these 2 entries to get that entry, well, this here is, well, we're going to row 5, so it's 5, choose 0, 1, 2, 3. So this guy is 5, choose 3. And we're adding the entries above here. So that's going to be 4, choose 2, and 4, choose 3. And there's nothing special about the position. We could do that anywhere. That's how to generate Pascal's triangle. But in general, what's going on here? So because position isn't important, we're really saying, well, if we have n choose k, that's kind of the entry that we're getting by adding the 2 above. The 2 above that we're adding is n minus 1 choose k, and n minus 1 choose k minus 1. And that we've proved. That's Pascal's identity. We've proved that in class. So that's great. So we can see that this is indeed binomial coefficients written in a triangle. Now, I will say this is the usual way that you've seen Pascal's triangle, but it's a lot more instructive to kind of write it as a right angle triangle. So I'll do that on the next slide. So here's Pascal's triangle rearranged as a right angle triangle. You can see the patterns a little bit better. And I wrote it in two ways. So first I wrote it using the numbers, and the second way I wrote it is using binomial notation. And we can start to notice some patterns here. So if we were in class, I would kind of get you guys to play around with this, but we're on video, so I'm just going to tell you a few of them. So the first one, I think we've proved this in class, but the sum of the rows is interesting. So if we sum this way, here we get 1. I'll write the sums in blue here. Then we have 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. Let's just do one more. 1 plus 4 plus 6 plus 4 plus 1, you can check if you like, is 16. So you can start to see a pattern of what's going on here, and indeed we've proved this in class. But what is this saying? For each n, if you add up and choose every possibility here, you get a power of 2. And what power of 2? Well, this is the first row. This is, sorry, I should say the 0th row. This is 2 to the 0. This is the first row, 2 to the 1. The second row, 2 to the 2, etc. So the pattern that we've noticed is something we've already proved, that if you add up all the way from, let's say, k equals 0 to n of n choose k, we get indeed 2 to the n. So that's our first pattern that we've noticed, and that we proved earlier. So there's nothing too special there, but that's our first pattern that we've noticed. Let's look at some more. So another one that you might notice playing around with it after a while is that if you start summing on the diagonals, and you can stop kind of anywhere, but you have to start at the leftmost bit. Let's say if we do this diagonal, let's go 1 plus 2 plus 3 plus 4. And what do you get? Well, you get 10. And 10 is the number directly below where you've stopped. And this kind of happens with any diagonal. Let's do this one in blue. 1 plus 1 plus 1 is indeed 3. That looks good. Let's look at maybe one more. 1 plus 4 is 5. And maybe let's look at kind of a long one. 1 plus 3 plus 6 plus 10 plus 15. If you add them up, you'll indeed get 35. And you can check that that would indeed be the entry in the next row of Pascal's triangle. So I wrote Pascal's triangle in both ways so we can kind of see what's going on with binomial coefficients, so we can start to see how to prove this result. So let's think of these in terms of binomial coefficients. So let's look at this red one. So let me highlight this in the binomial Pascal's triangle. So we have 1 choose 0, 2 choose 1, 3 choose 2, 4 choose 3. And if we add those together, we get indeed 5 choose 3. And let's look at maybe the yellow one as well. So 2 choose 0, 3 choose 1, 4 choose 2, 5 choose 3, and 6 choose 4. That's going to give us indeed, you can check that that's, oh, wrong thing. That is 7. Oh, 7 choose 4. Great. I'll color this in yellow, actually. There we are. So we can start to make a conjecture about what's true here. So it looks like If we start at 2, choose 0, and we add, say, these 5 terms where each of the top and the bottom of the binomial coefficient goes up by 1, then we get 7, choose 4. So we get, indeed, just 2 plus the number of terms that we've added. So that's 2 plus 5 is 7. And we're choosing kind of the last thing that we go up to. We can see that that's true in this one as well. So if we start at 1 and we add up 4 terms, we get the next one, 5, choose 3, since that's the last thing that we wrote down here. So our conjecture, and we're going to prove this, is that if we sum, and we'll say like j here is going to be the bottom term of, or the bottom number in the binomial. So we start at 0, and let's go up to, let's say we're going up to r, just to pick a number. So in this case, we're going from, in the yellow case, we're going from 0 all the way to 4. So r in this case is 4 in the yellow case. Well, what are we adding up? We're adding up, well, we're starting at some numbers. We have to pick a number here. Maybe we'll call that k. So we start at k, choose 0, and then we do k plus 1, choose 1, k plus 2, choose 2. You can see here, it's 2, choose 0, then 2 plus 1, choose 1, 3 plus 1, 2 plus 2, choose 2, 4, choose 2. So we're doing k plus j, choose j. And the sum of those, what's that going to be? That is going to be, you can see down here, we're going to have one more than our last number here. So that's going to be our last term as we go all the way up to r. So it's going to be k plus r. And we're going to have one more than that. So it's going to be k plus r plus 1. And the choose here is going to be the last thing that we wrote down. So it's going to be r. So that's our conjecture from what we've noticed in the triangle. And let's say here we need that k and r are both non-negative, and that should be fine. Okay, on the next slide, let's prove this. All right, let's induce on r. So r is going to be the thing that we care about. So our base case, or let's write down induction on the variable r. So the base case is going to be the smallest case when r is 0. So what do we have? We have j equals 0 to 0 of whatever k is, k plus j, choose j. Well, there's only one term here when j is 0, so this is going to be k, choose k plus 0, choose 0, so that's k choose 0, which is 1, and that equals k plus 0 plus 1, choose 0, because remember here r is 0, and that's also 1. Anything choose 0 is 1. So our base case holds. Now let's do the inductive case here. So I'll write down our assumption. So we're going to assume that this holds from j equals 0 to, let's say r of k plus j. Choose j, let's say that equals k plus r plus 1, choose r. So let's say it holds there, and we want to show that it holds for r plus 1. So let's to show, we want to show that if we replace r by r plus 1, it holds. So it's going to be k plus r plus 1 plus 1, so k plus r plus 2, choose r plus 1. So that's what we want to show. So we'll start on the next slide with the left-hand side here, and we'll show that indeed, using our inductive hypothesis, that we can indeed do some algebra to get it looking like the way we want. So let's consider that rth plus 1th sum. And all we're going to do is we're going to split off the first r, or I should say from 0 to r, those terms. We're going to use our inductive hypothesis, and it's going to be fairly straightforward here. So this is going to be the same thing as the sum from j equals 0 to r. So those terms up to r of k plus j, choose j, and then we'll write the r plus 1th term separately. So that's going to be k plus j is now r plus 1, so k plus r plus 1, choose r plus 1. And by our inductive hypothesis, we're saying that this is k plus r plus 1, choose r plus k plus r plus 1, choose r plus 1. So this here is by our inductive hypothesis. Maybe I'll highlight that too, just so you know what we're doing. That's what we assumed on the last slide. Now maybe pause the video and see if you can reason why this pretty much finishes our problem, what the next step is. And once you get that, continue on. Okay, so hopefully you realized that we can use Pascal's identity here. So we don't even need to kind of expand these out in terms of factorials. We could if we wanted to, but we already have this identity out for us. We know that if we have something, choose r, and the same thing, choose r plus 1, well, by Pascal's identity, that indeed is just the next something. So k plus r plus 1 plus 1, so k plus r plus 2, choose r plus 1, and that's by Pascal's identity. So in this case, we have our n is k plus r plus 1. So we have n choose r plus n choose r plus 1. If we add them together, we get the next one, n plus 1 choose r plus 1. So that's just using Pascal's identity, and we're done. So that's the next identity we've noticed from Pascal's triangle. Let's look at one more. So the next identity I want to talk about is quite interesting. It's called the Star of David identity. And it looks more like a Star of David in kind of the traditional Pascal's triangle. You can see you just pick an element to center it on. It could be any element you want. And if you look around that, you get 6 points. There's like a hexagon. And you can make a Star of David by connecting every second one to make triangles, and they're kind of overlapping triangles. Well, the Star of David identity says that if you multiply those elements at each point on each triangle, you get the same thing. So here we get 3 plus 4 plus 10 is 120, and 3 plus 4 plus 10 is 120. This one was fairly symmetric, so it wasn't super obvious. But if we look at a different one, maybe let's look at, we'll write down one more row to kind of help us out. 1, 6, 15, 15, 15, 20, 15, 6, 1. So maybe let's center this indeed at this 5. So let's center it. So that was the 6 that we centered on. Let's center it on this 5 this time, and let's see what's going on. So here we get 4. Oh, I don't want that. I want this. So 4 times 1 times 15. That's going to be the same thing as 1 times 10 times 6. And you can check that. Indeed, you both get 60. So 4 times 1 times 15. 4 times 15 is 60. And 10 times 6 times 1 is also 60. So you can check this a few times and make sure that you understand what's going on here. But let's see if we can figure out what's happening in terms of binomials so we can write it down. So we pick a center one. So let's say the center one we pick is n choose k. So let's say that this guy here, we centered on the 6. So we're thinking of this as indeed, this here is n choose k. Then, what are we taking? We're taking, indeed, let's look at the red one. So that's going to be 1 less in the top and 1 less on the bottom. So this is n minus 1 choose k minus 1. This is n choose k plus 1. And the one right below it, n plus 1 choose k. So the red one is we want to show that n minus 1 choose k minus 1 times n choose k plus 1. That's the one just to the right of the one you're centering it on. And the one just below is n plus 1 choose k. We want to show that that equals, we'll do this in blue. So what do we have here? The one just above is n minus 1 choose k. So that's n minus 1 choose k. The one directly to the left of the center is n choose k minus 1. And the one to the lower right is n plus 1 choose k plus 1. So that's what we want to show here. So this one isn't too bad. Maybe pause the video and see if you can show that this identity holds, and we'll do it on the next slide. So pause, give this one a go. So hopefully you've seen that if you just write this out in factorials, both expressions, you get the exact same thing. So let's just go and do this. So this is going to be, the first one is n minus 1 factorial choose k minus 1 factorial, and then n minus 1 minus k minus 1 factorial. So that's going to be n minus 1 minus k plus 1, so n minus k factorial. The second one is n factorial over k plus 1 factorial times n minus k plus 1, so n minus k minus 1 factorial. And then finally, n plus 1 factorial over k factorial, and then n plus 1 minus k, which I'll write as n minus k plus 1 factorial. So those three things multiplied together. And if we do the blue one, you'll see it's very similar. We get n minus 1 factorial over. And maybe as we go, I'll highlight the terms that we have. So this is going to be k factorial, and this is going to be n minus 1 minus k, so n minus k minus 1 factorial. So above, we have, there's our n minus 1, we have that. There's our k, we have that. There's our n minus k minus 1, we have that. And similarly, we just keep going. So we have n factorial over k minus 1 factorial, n minus k minus 1, so n minus k plus 1 factorial. And there's our n factorial, there's our k minus 1 factorial, and there's our n minus k plus 1 factorial. And unsurprisingly, we get n plus 1 factorial over k plus 1 factorial, and then n minus 1 minus, n plus 1 minus k plus 1, so that's n minus k factorial, and that's what we have left over. Sorry, I want this. N minus k, oh, we have our n plus 1, and k plus 1, k plus 1. So you can see we have the same things written out, so these are obviously the same expression. So that's the Star of David identity, another identity involving Pascal's triangle. So one more identity I want to talk about is the following. We added on one diagonal. Let's see what happens when we add on the other diagonal. So let's go ahead and do it. So let's add on this diagonal. So here we just get 1. And then here we also get 1. Maybe write this in green, 1. And then let's do the next diagonal. We get 2. Let's do the next diagonal. We get 3. Let's do the next diagonal. We get 5. Let's do the next diagonal. Hopefully you can see what's going on here. We get 8. And let's do one more diagonal. Hopefully you've noticed this pattern. If we add those together, we indeed get 13. And this should look very familiar to you. It looks like the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, 13. You could check that the next one would indeed be 21. So what is the Fibonacci sequence? Let me kind of remind you guys. So the Fibonacci sequence, it's something that's defined recursively. So they tell you what kind of the first elements are, and maybe we'll call it F0. F0 is 1, F1 is 1. And then we can generate any next element, let's call it Fn plus 2, by adding up the previous ones. Fn plus 1 plus Fn. So you can see what's going on here. We're defining F0 and F1. Then F2 is just F0 plus F1. 1 plus 1 is 2. F3 is 2 plus 1. F4, which is 5, is 3 plus 2. F5, which is 8, is 5 plus 3. F6, which is 13, is 8 plus 5, and it keeps going. Now that's nice to notice, but we have to prove, indeed, why it's true. So let's see if we can write this conjecture in terms of factorials. So here we have 0, choose 0, and then this next one is just 1, choose 0. And here we have 1, choose 1, and 2, choose 0. Here we have 2, choose 1, plus 3, choose 0. And here we have 2, choose 2, plus 3, choose 1, plus 4, choose 0. So it looks like, in some sense, these are all of the things, all of the terms where 0, if we add these two things, we get 0. This is all of the terms where if we add these two numbers, we get 1. Here's all the numbers. If we add the two numbers, we get 2. If we add the two numbers, we get 3. If we add the two numbers, we get 4, etc. So let's kind of write that down. So here's our conjecture kind of written in two ways. So remember we were saying that, well, if you add all of the numbers in your combination, in your binomial coefficient, you get n. If you add all of those cases, you get the nth Fibonacci number. So that means, well, we're summing up all cases where r plus s equals n of r choose s. Or we can write it kind of the other way, right? We can write it more indexed from r equals 0 all the way up to n of n minus r choose r. You can check that these indeed are the same thing. So here if r was 0, we get 0 plus n. Well, maybe actually s is operating like r here because it's here, in fact, let me erase that. It's not going to make a difference here. I'm going to write this as S choose R. Doesn't make a difference, of course. But if R is 0, then we get, well, 0 plus n equals n. So this is n choose 0. And here, when R is 0, we get n minus 0. Choose 0, n choose 0. If R is 1, here we get 1 plus s minus 1. So it's going to be n minus 1, choose 1. And here, if R is 1, we get n minus 1, choose 1. So it's the same thing, just written in slightly different notation. So that's our identity, but the proof I'm going to leave as an assignment question for you guys. So you will see this as an assignment. And I'll step you through it. We'll prove something. We're not going to prove this directly, but we're going to prove a different problem that is a bijection to this, which is very interesting. Another thing we can think about doing is encoding Pascal's triangle into a matrix structure. Whenever you have a table like we do, you can think, well, I have a lot of machinery from linear algebra lying around, so maybe it is a good idea to think of this as a matrix. So I'm going to encode it the way we did here. I'm going to call this, if you like, let's call this L3. L for lower triangular, and 3 for the fact that we have the 3 choose R row here. So that would be L3. And for example, L0 would just be the matrix with a 1. And let's say L2 would be 1, 1, 1, 1, 2, 1 with some zeros here. And in fact, a lot of the times, because there's going to be a whole triangle in the upper bit of the matrix in the upper right, that's going to be zeros. Sometimes I just won't write these. Any entry that isn't written down, we're going to think of as just being 0. So maybe I wanted to write L2 with no 0. So that would be fine. It would mean the same thing. And in general, maybe we can write Ln as, well, write it like this. 0, choose 0, 1, choose 0, all the way down to n, choose 0. And here we're going to have n, choose 1, n, choose 2, all the way to n, choose n. And on the diagonals, of course, we're going to have things like 1, choose 1, 2, choose 2, etc. So hopefully that's clear what I mean by Ln there. So maybe, let's see what happens when we multiply this following vector by Ln. And it'll be 1x, x squared, all the way down to x to the n. And maybe pause the video now and see if we can work out kind of what's going on here. It's quite interesting. I will say, when you get an expression, try and factor it, and that will kind of clue you in. Okay, so if we multiply this, so here we're going to get 1 times 1, and all these are zeros, so we get 0 times the rest of it. So up here, we just get 1. That's nothing particularly interesting. Let's look at the next one. Here we have 1, choose 0 times 1, so that's 1. And 1 times 1, which is 1, times x, and then the rest are zeros. So we're going to get 1 plus x. Now let's look at the next one. This would be 2 choose 0 times 1. And anything choose 0 is 1, so we have 1. And then we have 2 choose 1 times x. 2 choose 1 is 2, so we're going to get 2x. And then we're going to get 2 choose 2 times x squared. So that's 1 times x squared. So we get x squared. And here we're going to have 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3 times 1x, x squared, x cubed, respectively. So we're going to get 1 plus 3x plus 3x squared plus x cubed. And that'll keep going. You can kind of see what's going on here. And then hopefully you notice that all this is the expansion of 1 plus x to the n. So all of these, this is 1 plus x to the 0. This is 1 plus x to the 1. 1 plus 2x plus x squared is 1 plus x squared. 1 plus 3x squared plus x cubed is 1 plus x all cubed. And it keeps going like that. So that's pretty interesting. We can see what this kind of matrix does, writing Pascal's triangle in terms of this lower triangular matrix. So that's quite interesting. So now that we have Pascal's triangle written in terms of a matrix, maybe it's a good idea to ask, what are some matrix properties of this Ln? Well, a very easy one's the determinant. Well, if you remember, all of these Ln's just have ones on the diagonal, and this is a triangular matrix. So whenever you have an upper triangular or a lower triangular matrix, you can find the determinant just by multiplying along the diagonals. You could imagine, if you wanted to, doing some sort of cofactor expansion, but it turns out you can just multiply on the diagonals. And you can see with all of these guys, we're indeed just going to get 1. So that's nice. The determinant of any of these Ln's is 1. Well, what's another interesting thing about matrices? Well, inverses. Let's see if we can figure out the inverses for each of these and see if we notice a pattern. Once we notice a pattern, maybe we can start to prove what the inverse of each of these matrices is. So, pause the video now and see if you can work out the inverse of each of these matrices. Okay, now that we're back, hopefully you could see that the inverse of L1 was 1, 1 on the diagonal, and then a negative 1 here. And remember, anytime I don't have an entry, I do mean a 0. L2, you should have seen we got 1, negative 1, 1, 1, negative 2, 1. And then L3 inverse, we have 1, negative 1, 1, 1, negative 2, 1, and let's make this a little bigger. Negative 1, 3, negative 3, 1. So you can kind of see what's going on here. So it looks very similar to the original matrix, except whenever the sum of the indices is odd, we have a negative. So it's very similar. Let's see if we can write our conjecture up, and then we'll talk about what we need to do to prove this. So our conjecture is that it's a lot like Ln, except we have these negatives in places where the sum of the entries is odd. So you can think of that in the following way. So for each term, it's going to be each term here, just let's say an arbitrary term, and let's say k choose r. So for a k choose r term, we're going to have negative 1, and we want it negative when the sum is odd and positive when the sum is even, and that can just be done by adding together k and r. So that's kind of an arbitrary term inside of this matrix. And on the next assignment, you'll be asked to show that the inverse of Ln times Ln itself does indeed give you the identity matrix, which means that this is the proper inverse. So that you'll be asked to show on your assignment.